In this section, we're actually going to talk about how to solve problems involving mixed constraints. So in an earlier section, we talked about how you could solve maximization problems as long as they have all less than or equal to constraints. Then we talked about how you could solve minimization problems as long as they had only greater than or equal to constraints. But obviously there are going to be some situations where we have mixed constraints and there's nothing we can do to get the problem into one of those two standard forms that I've already shown you. So first thing I'm going to do is I'm going to just set up a couple of word problems here. Now this website here is actually a website that will allow you to solve linear programming problems. You just have to read the small print and determine how to put them in. But actually, it'll actually bypass all of the work. But as you know, that's not going to help you on the test to just be able to have something solve them. But it is helpful to know that there is a linear programming calculator out there in the real world that can be used to solve problems. Alright, let's look at a simple one to set up. So right here it says an individual on a high protein low carb diet requires at least 100 units of protein and at most 24 units of carbohydrates. The diet will consist entirely of three special liquid foods, A, B, and C. And the contents and the cost of the foods are given below. How many bottles of each brand of diet food should be consumed daily in order to meet the protein and carbohydrate requirements at minimal cost? And what is the minimal cost? Now we're just going to set up the model for this. We're not going to solve it. If you wanted to, you could write a table out here and you could see that each bottle of food here has, or liquid diet food has 10 units of protein for bottle A, bottle B has 10 units of protein, and bottle C has 20 units of protein. And then bottle A has 2 units of carbs, bottle B has 3 units of carbs, bottle C has 4 units of carbs. So if we let X1, X2, and X3 represent the number of bottles of brand A, B, and C that are consumed, then we can use this table here in order to determine our objective function, because the bottom row of the table tells me how much the cost of each bottle is. So if I want to minimize my cost, I know I need to minimize this function, 60 cents times each bottle A, plus 40 cents times each bottle B, plus 90 cents times each bottle C. And then we've got to have at least 100 units of protein, so that means the amount of protein has to be greater than or equal to 100. And we get 10 units of protein per each bottle A, 10 units of protein per each bottle B, and 20 units of protein per each bottle C. And if you go back and read the problem up here, it says that we have to have at most 24 units of carbs. So we want to make sure that our carbs are less than or equal to 24. So looking at our table, I see I get 2 units of carb per bottle A, 3 units of carb per bottle B, and 4 units of carb per bottle C. And I need that to be less than or equal to 24. And then you put your non-negative constraints here. X1 through X3 has to be greater than or equal to 0. Now that's the linear programming model, but actually this is not in standard form, because if you were minimizing, you want all your constraints to be greater than. Well, this problem actually could be solved using the dual method, but you would have to rewrite the second constraint. So let me show you down here. You would have to multiply everything in the second constraint by -1 to convert it to a greater than or equal to. So this is a linear programming problem. In other words, this is a standard minimization problem, but here it's not in standard form. To get it in standard form, you have to make sure all your greater than, all your inequalities are greater than. So now it's in standard form. Now there's going to be some other problems that we see that we can't write in standard form, so we're going to actually have to have another method to solve them. This problem could actually be solved using the dual method, but some other problems we wouldn't be able to solve using the dual method. This next example is a practical problem where 3 towns are forming a consolidated school district with 2 high schools. And we have a lot of constraints here. Each high school has a maximum capacity of 2,000 students. Town A has 500 high school students, Town B has 1,200 high school students, and Town C has 1,800 high school students. The weekly costs of transporting a student from each town to each school are given in this table down here. And in order to keep the enrollment balance, the school board has decided that each high school must enroll at least 40% of the total student population. Furthermore, no more than 60% of the students in any town should be sent to the same high school. How many students from each town should be enrolled in each school in order to meet these requirements and minimize the cost of transportation? So what I've done here is I've just said, well, since the cost is based on all the 6 different transportation routes, let's let each variable represent a different transportation route. So I'll let x1 be the number of students transported from town A to school 1, and x2 the number transported from town A to school 2. Then I'll let x3 be the number transported from town B to school 1, and x4 be the number transported from town B to school 2. And then finally I'll let x5 be the number transported from town C to school 1, and x6 be the number transported from town C to school 2. And what you might want to do is draw a diagram, and I've drawn a diagram here where the 3 circles are the 3 towns and the 2 rectangles are the 2 schools. And notice that I've drawn arrows from town A to school 1 and town A to school 2, and I've labeled them x1 and x2. And then from town B to each school I labeled x3 and x4, and then from town C to each school I labeled x5 and x6. So that just gives you a visual that might be helpful. Now the objective function is actually pretty easy to set up, because you know you want to minimize cost here, and you know the cost from town A to school 1 is $4 per student. I'm just getting this from this table up here. The cost from town A to school 2 is $8 per student. The cost from town B to school 1 is $6 per student. From town B to school 2 is $4 per student. From town C to school 1 is $3 per student. And from town C to school 2 is $9 per student. So that's our objective function. If you add all these up, that will represent your total cost. Now, one of the things that we have to do here in this problem, we're going to introduce equal to constraints, because we know we have 1,200 students at town, we have 500 students in town A. So we have 500 students in town A, 1,200 students in town B, and 1,800 students in town C. And in this case, we want to make sure that the students that we transport from town A add up to exactly 500. And we want to make sure the students that we transport from town B add up exactly to the 1,200 students that are there, and the students transported from town C add up to exactly the 1,800 students that are in town C. So that will give us 3 equal to constraints. x1 plus x2 equals 500, that's the students from town A. x3 plus x4 equals 1,200, the students from town B. And x5 plus x6 equals 1,800, and that's the students from town C. And then each high school actually has a maximum enrollment of 2,000 students. So the number of students that come into each high school has to be less than or equal to 2,000. So if you look at school 1, you'll see the students that come into school 1 are x1 plus x3 plus x5. So x1 plus x3 plus x5 must be less than or equal to 2,000. But the same is also true for school 2, and the students coming into school 2 are x2 plus x4 plus x6. And so that has to be less than or equal to 2,000 as well. So that gives us 2 more constraints, x1 plus x3 plus x5 less than or equal to 2,000, x2 plus x4 plus x6 is less than or equal to 2,000. We also have another constraint that says each high school must enroll at least 40% of the student population. Well, if you calculate 40% of the student population, if you add up the total number of students, 500 plus 1,200 plus 1,800, you get 3,500 students. And so 40% of the total 3,500 would be 1,400. So that tells me that the number of students going into school 1, x1 plus x3 plus x5, must be at least 1,400, which is greater than or equal to 1,400, and the number of students going into school 2 must be at least 1,400, and that would be x2 plus x4 plus x6. So that gives me these two constraints here. And then the last constraints are that no more than 60% of the students in any town should be sent to the same high school. So this actually puts a constraint on each one of your variables. So the number of students that go from town A to school 1, in other words x1, must be less than or equal to 60% of these students. Now 60% of 500 is 300. So the number of students that go from town A must be less than or equal to 300, but also the number of students that go from town A to school 2 must be less than or equal to 300. And then if you find 60% of 1,200, that'll tell you that the number of students that go from town B to school 1 must be less than or equal to 720, and the number of students that go from town B to school 2 must be less than or equal to 720. And then for town C, get 60% of 1,500, or let's see, is it 1,500? Oh no, 1,800. So 60% of 1,800 must be 1,080. So the number of students that go from town C to school 1 must be less than or equal to 1,080, and the number of students that go from town C to school 2 must be less than or equal to 1,080. And then if you put all of those together, you get x1 must be less than or equal to 300, x2 must be less than or equal to 300, x3 must be less than or equal to 720, x4 must be less than or equal to 720, x5 must be less than or equal to 1,080, x6 must be less than 1,080, and then all of your x's must be non-negative, because you got to have your non-negative constraints. And so that's how we set up that linear programming model. And you can see in this model we have 3 different types of constraints. We have equal to constraints, we have less than or equal to constraints, and we have greater than equal to constraints. So again, we're not going to solve that. That was just a practice at setting up a very practical linear programming problem. So I'm going to leave you with this problem to practice on, and so freeze the video and see if you can set up the linear programming problem for this one, and I'll kind of walk you through it. Once you read the problem, you can see that I said x1 is the number of home to roost birdhouses to store 1, x2 is the number of flying home houses that go to store 1, x3 is the number of home to roost houses to store 2, and x4 is the flying home houses that go to store 2, and x5 is the home to roost houses that go to store 1, x6 is the flying home houses that go to store 3. So I'm sorry, this is home to roost to store 3, and this is flying home houses to store 3. And then you've got to set up, since if you read the problem, they want twice as many home to roost birdhouses than flying home houses. So that tells us x1 has to be 2x2, and this is for store 1. Store 2 wants twice as many home to roost birdhouses than flying home birdhouses as well. So x3 would have to equal 2x4. And then store 3 wants an equal number of each type, so x5 would have to equal x6. And then you have space for no more than 20 birdhouses at store 1, so x1 plus x2 has to be less than or equal to 20. And then no more than 16 birdhouses at store 2, so x3 plus x4 must be less than or equal to 16. And then store 3 needs at least 9 birdhouses, so x5 plus x6 has to be greater than or equal to 9. So if you put this in a linear programming problem, you're going to be maximizing this function, because this is the cost of each birdhouse, and then these are the constraints that I just listed up here. And one thing you could do here is you could actually take the x1 equal 2x2 and write it as x1 minus 2x2 equals 0. That gets all your variables on the left. And then you could also do the same thing for this equation and this equation, and then you would write it that way. You'd be able to write the problem with all your variables on the left. So now again, in this video I was just showing you how to set up these word problems, and in the next video I'm going to show you how you can solve these problems that have mixed constraints in them using the modified problem.